All right, tonight what we're going to be talking about are the different types of intermolecular forces that exist between different molecules. And as you remember, a molecule can either be an element or a compound, but it's things that have bonds. So there are two types of forces that exist within a molecule, and one is known as the intramolecular force, and the other is the intermolecular force. Intramolecular forces are the forces that keep the individual molecules together. So it's what connects one atom to another atom. How we refer to them in this class typically is they are the bonds. An intermolecular force, on the other hand, is the force that attracts one molecule to another molecule. And intermolecular forces are what keep solids as solids and liquids as liquids. And we'll be discussing this a little bit further as we go on. What I want you guys to remember is intra versus inter. If you know about anything about roads, there are intrastates and there are interstates. An intrastate is a road that is within the same state. That is why you're talking about an intramolecular force, is the forces that are keeping one molecule together. An interstate, on the other hand, is a road that goes between states. So therefore, an intermolecular force is the attraction that exists between one molecule and another molecule. So here's a visual of an intra versus an inter. Intramolecular forces are these lovely bonds. So if I want to break these force or this attraction that exists between each other, I would be breaking bonds. And note the energy, 415 kilojoules. Intermolecular forces, on the other hand, is that the attraction that exists between one molecule of water and another molecule of water. Often how we draw this attraction is a dashed line. That dash means it's not truly a bond, but it is showing some sort of an attraction. Bonds, remember, are solid lines. If I broke this attraction, even though it does take some energy to do that, notice this is only 41 kilojoules. So for water, it is 10 times less energy to break an intermolecular force as an intramolecular force. One teacher used to say that her comparison for intra versus intermolecular is if somebody's hanging off of a building and you're holding hands, you versus that other person where you're holding hands would be known as the intermolecular force. So if you broke that bond, they would slip. Okay, their hand would be released. An intramolecular force is if you broke your own individual arm off, kind of a thing. So it's an intramolecular force versus an intermolecular force is within the same body, I guess, is her thing, or within bodies is what she's talking about for intermolecular forces. All right, there are four types of intermolecular forces that you're going to need to identify and figure out the characteristics for. The first one is for ionic compounds. And ionic compounds, if you remember, are ions. And what is an ion? An ion is something with a positive or negative charge. As you know, positives and negatives are attracted to one another. And so what's going to happen is that when something becomes positive, meaning it lost an electron, it is going to be attracted to something that became negative by gaining an electron. And so this attraction that exists between the two different elements or two different compounds is because of different charges, because they're positive versus the negative charge. This is the strongest intermolecular force that exists that we will be studying in this class. Now, how you need to identify that a compound would exhibit an ionic or an ion-ion interaction is because it would be an ionic compound. So how do we do that? If you remember from previous units, Na is a metal, Mg is a metal, and K is a metal. So all you have to do to identify something that would have an ion-ion interaction is look at the first element. If it is a metal, it is going to be an ionic compound, and all ionic compounds have ion-ion interactions. So this would be one thing that I would look at straight away. Does it start with a metal? If it does, it would be an ionic or an ion-ion interaction. All right, looking at why they're so strong, if you note one Na positive, so we've got this one Na here, what I'm going to do is I'm going to look at it. Well, It exists by itself as Na with a positive 1, and if you look at it, it is surrounded by negatives. Every single side of that positive is surrounded by a negative, which means that interaction is extremely strong. So ion-ion interactions exist within an ionic compound, and they are extremely strong because they are entirely surrounded by the opposite charge. All right, so that's ionic compounds, and there are 3 types of forces that could exist within a covalent compound. So if you have identified it as an ionic, it will have ion-ion interactions. If it starts with a nonmetal, then you are going to have to deal with the other 3 types of forces that exist, and that would be if it's a covalent compound. The first one that you're going to need to know is dipole-dipole forces. So what does di mean? Well, if you remember from your prefixes, di is 2, and pole means that it is a polar or it's got some sort of polarity with that pull of electrons. So what is a dipole-dipole force? What type of compounds would that be shown in? Well, that is found in polar molecules. And so the example that I give you is NF3. Well, why do dipole-dipole forces exhibit or exist? Well, if you look at it, what's happening in a dipole-dipole or a polar compound, okay, so dipole-dipole is between 2 polar compounds. You're going to look at it. A polar compound will have a positive end and a negative end, okay, partial positive, partial negative end. Well, what is this partial negative end going to be attracted to? Well, it's going to be attracted to the partial positive end of another polar compound. So if you look at this attraction would exist because these charges are opposite. And just like with the ionic compound, where opposite charges were attracted to one another, here opposite charges are attracted to one another. It's just not an entirely given and taken. It's just more of a semi, where that 70-30 that I had talked about. So because it's not 100%, it's not as strong as an ionic compound, but it still is relatively strong. Now, if you look down below, what's happening is that this is showing where things are repelled, and I'll show that in a yellow. So why is this repelling each other? Why is this repelling each other? Why is this repelling each other? Well, if you look at their charges, all of those are interactions between the positive end of one particular compound and the positive end of another particular compound. On the other hand, if you look at this interaction, that is an attraction. Here's an attraction. Here's an attraction. And why is that an attraction? Well, if you once again look at them, your charges are opposite. So one has a partial negative, and it is attracted to the partial positive of another compound. All right, hydrogen bonds. Hydrogen bonds are a special type of dipole-dipole interaction, and you do have to be specific on it. So just because it is a dipole-dipole, if it also has hydrogen, you need to note that it actually would have a hydrogen force or hydrogen bond as opposed to a dipole-dipole moment. And what happens with a hydrogen bond is these are relatively easy to identify, and I would recommend looking for these second. It is when a nitrogen, oxygen, or fluorine are directly connected to a hydrogen. So hydrogen bonds, they are hydrogen that is directly between all of your FON molecules or FON elements. FON, so fluorine, oxygen, and nitrogen. So if you have a hydrogen that's connected to any of those, you are going to have a hydrogen bond. Now note, as I said in the notes, this is not a real bond. It is not literally one hydrogen that is being in one particular compound being bonded to another nitrogen or oxygen or fluorine in another molecule. It is just a really strong attraction. So that's kind of why they say hydrogen bond, because that bond is a stronger attraction than usually IMFs have. All right, so looking at this, if you note, hydrogen bonds, remember, are only between hydrogen and a fluorine, oxygen, and nitrogen, and they literally have to be connected to them. It's not that it has both of those elements in the compound. The oxygen has to be connected or bonded directly to that fluorine, oxygen, or nitrogen. All right, so looking at this, we've got this is the attraction that exists for a hydrogen bond. So we have a one water molecule that has a partially negative end and a partially positive end on those hydrogens. The negative is on that oxygen. And what it is it's the attraction of these lone pairs to this partially positive hydrogen. And these lone pairs attracted to that partially positive hydrogen on another water molecule. Here's the hydrogen one down to the lower left, and if you notice, it's attracted to the lone pairs of that oxygen, and this hydrogen's attracted to that lone pairs of the oxygen. And this primarily comes about, this hydrogen bond, because they are attracted to the lone pairs that are found on the nitrogen, fluorine, and oxygen. All right, what I want you to note on this one is that hydrogen bonds can exist between any type of molecule as long as your hydrogen is always bonded to either your F, your O, or your N. So in particular, let's look at this one over here. The nitrogen or the hydrogen is attached to a nitrogen in this case, but the hydrogen on the right is attached to a fluorine. Well, because both of them are, fluorine and nitrogen, are part of the elements that are available to do hydrogen bonding, you are okay, and these molecules would have an attraction that would exist as a hydrogen bond. All right. Another type of bond is London dispersion forces. And what that is an attraction force that arises for temporary dipole induced molecules. What another thing is that, what I want you to note is that London dispersion forces exist between nonpolar molecules, or two nonpolar molecules. Well, if you think about it, a nonpolar molecule has no pull. Why? Because the electrons are evenly distributed. But if you know anything about electrons, electrons are constantly moving. And if you give them a long enough time, what's going to happen is that they're going to be moving, and they might be sighted more towards one side of the molecule than the other, because they're constantly moving back and forth. So at one particular moment in time, it may have gone more towards one side of the molecule than the other and not be perfectly split. So that's what happens in this case. If you look at your electrons, they are primarily on the left-hand side. And when you do that, what happens is it creates a temporary dipole moment. And why? Because more electrons are found on the left of that molecule, so therefore it would be more negative on that left side, and on that right side, because it lost all of its electrons, or a lot of its electrons, it would become slightly positive. On the other hand, the molecule on the right has no dipole moment at the time because the electrons are evenly distributed. Well, what happens though is because this particle on the left is slightly positive, the electrons on the particle on the right are going to be more attracted to that particle. So what happens is that all of the electrons rush over to the left because they are attracted to that positive charge of that particle on the left, because all the electrons on that guy had moved to the left for a temporary moment. So this right here is when they actually exhibit that attraction, because this side now has a positive and this side now has a negative. They will have that attraction that does exist between a dipole particle, or two polar molecules. All right, but once again, this is not how they like to exist, nonpolar compounds. So electrons are constantly moving. So after a very instantaneous second, basically, it's going to go back to how it normally is. All right, so relative strength, you are going to absolutely have to have this memorized. Ionic compounds will be the strongest IMF, meaning that you will have to put the most energy in order to break those attractions. Then comes hydrogen bonding, then comes dipole-dipole, and the last and the weakest is London dispersion. So you're going to be expected to identify the types of intermolecular forces that exist. My first recommendation is look to see whether it's an ionic compound. H is a nonmetal, so therefore you are not going to be dealing with an ionic compound, so that's out. Then what I think you should try to do is figure out, is that H directly connected to one of your FONs, so fluorine, oxygen, or nitrogen, to figure out if it's going to have exhibiting hydrogen bonding. Well, I look at H, that's good, that's promising because it has that hydrogen, but then I look at Br. Br is not one of your FON particles, so therefore I know it will not exhibit hydrogen bonding. So my next step is to try to draw it. So I've got hydrogen. After the last unit, you should know that hydrogen is going to single bond to that bromine, and you're going to draw out a structure that looks very similar to this. Knowing that, if you follow your rules for polarity, you're going to have to figure out, is this a polar molecule or a non-polar molecule? You should note that this is going to be a polar molecule going towards that Br. It is a more polar molecule going towards that Br. So because it is polar, it is going to have an IMF, or intermolecular force, that will be equal to the dipole-dipole. So I'm just going to write DD, so it's dipole-dipole. You should write it out. All right, so the first one is dipole-dipole because HBr is a polar molecule, so it will exhibit those dipole-dipole forces. On the other hand, let's look at HF, the next one. So first I'm going to look at H. Is it a metal? No, it's not, so I'm going to move on. Is hydrogen directly connected to F, O, or N? Well, in this case, I only have a hydrogen, which is promising, so I possibly could have hydrogen bonding, and then I have it connected to that F. Well, there are no other elements, so I know that hydrogen has to be connected to fluorine in this case, so this would instantly exhibit hydrogen bonding. I didn't even need to draw the structure because by process of elimination, I know that hydrogen has to be connected to that fluorine, so we're going to move on. All right, CH4, first thing you check, is this a metal? It is not, so therefore it is not going to be the ion-ion interaction. So what is it? It's a nonmetal. So I'm going to check hydrogen. Once again, it has hydrogen, but if I look at it, I know that C is not F, O, or N. So therefore it cannot be hydrogen bonding. So I'm going to have to figure out the structure and figure out whether it is a polar or a non-polar compound. Without even having to draw it, I know that this is a hydrocarbon. It is only carbon that is attached to hydrogen, so I immediately know that this is going to be a non-polar molecule. As soon as I've identified that it is going to be a non-polar molecule, I know the only type of IMF that it can have is the London dispersion. Okay, so this has to be London dispersion. All right, SO2. Once again, check if it's ionic. It is not ionic because S is not a metal. Next thing is, do you have a hydrogen? No, we have no hydrogen, so I can't have hydrogen bonding. So now I need to figure out, is this polar or not? Well, I don't know off the top of my head, so I'm going to have to draw it. Remember, S will go in the center because it is written first, so therefore N is the least electronegative. After figuring out the Lewis dot structure, it would look similar to this. Okay, so now I'm going to have to figure out whether it is a polar or non-polar molecule. So I'm going to go through my 4 steps. Number 1, is it a hydrocarbon? No. So I'm going to move on. I'm going to figure out the shape. The shape is linear. Is it possible that it is polar? Yes, it is. So we're going to move on to the next thing. Is the central atom attached to different things? No, it is not. So this will be a non-polar substance. Okay, so once again, if it's non-polar, I look at my 4 types of IMF, and this has to be London dispersion forces. CH3OH. All right, so this one's going to be a little bit tricky. So I'm going to look at my first guy, and that is not going to be ionic because it's a carbon. So now I see, I'm going to check, is it hydrogen bonding? Well, I have a hydrogen, and I also have that O from my FON possibility. So I'm going to have to draw it out. So I have carbon in the center with its 4 lone electrons. I'm going to have hydrogen on the outside. Okay. And then I know hydrogen always has to be on the outermost side. And somehow I have to incorporate this oxygen. So looking at this, I'm going to have a structure that is going to single bond like this and single bond like that. Okay, so I'm going to just focus on this hydrogen and oxygen right here, okay, along with that individual single bond. Okay, that's an O. So looking at this, do I have a hydrogen that is directly bonded to an oxygen? I do right there, so this too would exhibit hydrogen bonding. Note that not all the elements have to be hydrogen and fluorine, oxygen, nitrogen. It can be some sort of combination, but you do need to make sure that your oxygen is directly bonded to a hydrogen, or your fluorine or your nitrogen is. All right, the last thing that we're going to be talking about is where are these IMFs seen with these heating cooling curves that we talked about last semester. Okay, first I want to revisit. When you have something that is rising in temperature, remember that that is when your temperature is changing and you are all the same state. So here, if this was water, this is a water heating curve. Everything while you are heating up to that 0 degrees is a solid. Everything when you are going from a solid to, when you are going from 0 to 100 is going to be water. That is your liquid. And when you are when you're rising your temperature over here, that is all going to be a gas. So once again, when you're undergoing a temperature change, they are all the same state. Okay, and what that means is actually when you are changing your temperature, you are changing the amount of kinetic energy that you are having. And if you know anything about kinetic energy is how fast are you moving. And so what are you changing when you are increasing your temperature? As you remember from last semester or previous units, you are increasing your temperature, you are increasing your speed. Okay, so here you are increasing your kinetic energy, your temperature, and your kinetic energy. Okay, so now we are going to focus on these guys. And what you are undergoing when you are going through a phase change, such as from a solid to a liquid of melting or from a liquid to a gas, we always talked about that you are spacing out your molecules more and more. Well, what you're actually doing is breaking those interactions, those IMFs, the intermolecular forces between the water molecules, and you are spacing them out. So if you remember from previous units, we talked about what are you doing to the particles when your temperature is rising? Well, you're making them go faster. And then we always said, hey, what are you doing while you are changing states? And what we always said is you are spacing them out more. And what we're doing is we're actually breaking those intermolecular forces that exist between your particles. All right, so that's what it's talking about here. I would like to, and remember we always talked about whooshies, they're just going faster. That's this one. If we were to draw a what's happening on this part, if this was a particle. So if I look at these particles, what we are doing is we are actually breaking this interaction right here, and we are separating them so that the particle on the right can go more in one direction and the particle on the left can go in an opposite direction. So when you are undergoing a phase change, you are actually breaking your intermolecular forces. All right, hopefully you have a basic understanding of IMFs, and we'll talk more about it later.